So differentials, the one thing I want you to notice for if a function is differentiable at all at a number c or x is equal to c, it means that I zoom in it's smooth there, it's differentiable, but it means if I zoom in very, very close at that point, as close as possible, keep zooming in, it will eventually look linear. If you tried that on a calculator, it doesn't matter how curvy the function is, it's going to look linear eventually. So that means then that we can use the equation of a tangent line for f of x at x is equal to c to approximate f of c. So like using the tangent, just like we did before, linear approximation. That's part of the reason why we can do that, especially if we're very close to the number. The tangent line oftentimes is much easier to use. If you recall the Leibniz, I can never pronounce that right, notation for the derivative function dy dx, it's equal to f prime of x, which is the Newton notation. If we can kind of mishmash those together, but to understand what the different pieces mean, the dy is called the differential of y and dx is called the differential of x. Similar to delta y and delta x, which are finite measurable quantities, and the differentials denote a change in respective values. So however, the differentials are infinitely small, immeasurable differences approaching, and then for some reason, this zero got like shifted over here. So let's write that there, zero, if I could spell, zero. We can treat them as individual quantities, and we can even solve for the equation dy dx is equal to f prime of x for f of for dy. And that's called the differential form. So essentially, we're solving for dy. So you take the derivative and multiply. Pretty straightforward. It's just computational. But to understand what is actually going on, the difference between dy and delta y. So I know that delta x is just change in x. The dx is also just change in x, and those two are often just equal to each other. So delta x is usually equal to dx, right? But to delineate the difference between delta y is actually f of x plus delta x minus f of x, the change in y of the actual function, where delta y is the change in y of the tangent line to the function. So there is an ever so slight difference. The difference between the two, you can calculate how far the error is off, for example, like how much the tangent line deviates from the function itself. That the way you calculate that is to compare delta y to dy. So if you look at the function over here, this piece here is, if I do some change in x, the actual change in the y function, that's delta y. But the piece here, the differential, calculates the dy, actually calculates the change in the y of the tangent line, not of the function itself. But because you can get so close, you can get the 2 points like q infinitely close to p and r infinitely close to p. The q and the r start approaching each other. So like if q and r get infinitely close to each other, that means this piece here, the error, the calculation error in there, let's highlight that, in there becomes smaller and smaller. So the closer you are to the tangent point, that becomes smaller and smaller. But there is a difference, just so you know. Dy is the change of y on the tangent line, whereas delta y is the actual change on the function. Okay, so if I wanted to put some of these in differential form, you're just going to take the derivative. In our case, this is, oh, I was almost going to fall for my own trick. It's the independent variable is t, so it's going to be dy dt is equal to 6t squared minus 8t plus 10. But in differentiable form, you then solve for dy. So dy is equal to 6t squared minus 8t plus 10 dt. Differential form also becomes important later when we end up taking integration. So like in unit 6, this becomes important, this notation. So it's worthwhile taking the time to do it. So I want you guys to pause the video right now and try the other two pieces. I already did them, so I'll erase here. So pause and try. This is what I got. I put the dx in the numerator. You can also write the dx here on the side if you like. Here on the last one. Dx, like that. Okay. Oops. I started this one. We'll look at that afterwards. All right. So for, we're going to compare delta y to dy. Remember, there's a difference. Delta y is the change on the actual function, and dy is the change on the tangent line, right? So how are we going to find? We're going to find dy, and then we also have to compare it against delta y. So in our case, it's going to compare. We're going to have to find dy dx, which in our case is 3x squared, and then it's going to be dy is equal to 3x squared dx, like that. So I'm going to find the value of dy. I'm being told, oh, I forgot to write the conditions. Hang on. Let's when x is equal to 1 and dx is equal to 0.01. So dy in that case is going to be equal to 3 times 1 squared. Delta x is 0.01. And that's equal to 0.03. So that is the change on the tangent line there. Let's compare that. So I'm switching. I'm going to find delta y instead. And delta y, remember, is f of x plus delta x minus f of x. So I need to find f of x plus delta x. So f of x plus delta x, x is, ooh, hang on, come on, buddy. There we go. Nope, not doing it. Let's see. There we go. It's going to be 1 plus delta x is 0. So delta y, and again, I forgot to write the conditions. When delta x is equal to 0.01 and x is equal to 1, so delta y is equal to f of 1 plus 0.01 minus f of 1, which is going to be 3. No, not 3. I'm taking the derivative. So it's going to be 1.01 cubed minus 1 cubed. And 1.01 cubed is, let's see, I have to put it in my calculator here, is 1.03001 minus 1. So that is going to be 0.030301. And I'm doing lots of decimal places because I'm comparing. So now you can see in this case that my delta x, in our case, it's underneath that the value is underneath the value for delta y. My dy, sorry, my dy is smaller than my delta y. So in this case, which makes sense because the cubic function looks like this here. So down here, I drew it, right? I have my two values here. So in this case, this is dx, which was equal to delta x. And from here to here, right here, that's my dy. That's that part there. And out here, that's my delta y. So my tangent line is below my actual function, so it makes sense that my dy will be lower than my delta y. So in this case here, the difference, this distance from here to here is actually 0.0000301, like that. So if I use the tangent line to approximate around here, it would be off by this much, by a tiny little bit. All right, so now you're going to do the same for the other one. As you can see, I started this one already. And let's see, I need to find delta y, which is equal to f of x plus delta x minus f of x. So in this case, when x is equal to 1 and, same as before, delta x is equal to 0.01, we end up with delta y equaling, and by the way, from the picture, I can already tell that my dx here, dx is equal to delta x, but my delta, or delta y, the actual function, is going to be smaller than my dy, because the tangent line is now above the actual function. So I know that I should be getting a smaller value for delta y than I got for dy. All right, let's see. I'm going to distract myself here. F of 1 plus 0.01 minus f of 1, which is equal to, the function was the square root, so I'm going to take the square root of 1.01 and subtract 1 from it. And I end up with, and I need to use my calculator again, the square root of 1.01 equals 1. This is going to be 0.0049888. And I'm doing lots of decimal places so I can see that there's an actual difference. So in other words, these are extremely close to each other. Since my delta y and my dy are almost the same value. So using that linear approximation would be very good and very close. The error is off by 0.0000022 or 21 or something like that. No, 12, sorry. All right, and that's the end.